and also for giving me the second chance. I missed the first one. So the topics that I have chosen for this presentation, seawater desalination and access to untapped water resources. This may not have directly any relation to the Department of Energy, but very important for all of us, since this world is becoming increasingly water stressed. So that's why, and I'm also working in the same area. And here I have mentioned seawater desalination, but I didn't mention anything about the technology. So I work particularly with the polymeric membrane to reverse osmosis membrane, which is presently used mostly, I will say, for desalination purpose. I also work in the same field. So I've chosen this topic. And one moment. Yes. So I said that 71% of the earth is covered by water. But out of that, only 3% is fresh water. And out of that 3%, only 1% is available for our regular use. We cannot use water in that way. So even if 71% earth is covered, still only very little is available for us. And the way the population is increasing, so you can see the statistics, 2.5 billion to 7.7 billion 2019. So there is a need, increasing need of fresh water. There is 64 billion cubic meter per year. This is a few years back, the data was saying. So most of the countries are becoming actually water stressed. So also India. So we say a country when water stress, when they extract more than 80% of their groundwater. Agriculture, that is the most demanding sector. The pie chart I'm showing here, that is showing that 38% of water is consumed, and this huge chunk, there is, okay, one moment. This part is a huge portion, probably 36% or 36. That is a drainage water. So what is water consumption? So when we are extracting water and utilizing, and that water, if cannot be utilized further for any other purpose, then that part is only consumed. Rest of the part is in a way wastage. Either it is drained or it is producing the wastewater. The second demanding sector is the municipality, where water consumption, you can see, is only 3%, but the wastewater generated is 8%. And industry, they consume only 3% fresh water, and the wastewater produces 16%. So most of the cases we have seen that water is not actually completely consumed. It's most 44% is consumed, so 56% is wasted. So when the world is becoming increasingly water stressed, we really cannot afford to lose this water, particularly fresh water. It reclaim, and reuse, all these things fine. But the demand, you see, it is 64 billion cubic meter per year, every year. So even after doing all these things, probably will not be able to meet the water requirement of the world. So what is the solution? The solution is the other part, not the fresh one. It is seawater. Seawater is plenty. It's a huge volume. So why can't we make use of the seawater? The seawater cannot be used directly. So other than this minimizing loss, regeneration, we need to see a new source, and that is sea. It's a huge source, and there comes a desalination technology. Now it may be a thermal technology, thermal-based technology, or it may be a membrane-based technology. So little bit about the history of membrane, since I am working in that area. I will also discuss and compare things with the thermal-based technology also. But I said that since membrane-based technology, They are increasingly becoming popular because of certain reasons that also I will discuss. So I thought, why not to say a little bit about the osmosis process. Though osmosis was known for a long time, I mean, but scientifically some kind of demonstration was given by this gentleman, J.A. Nollet, in the year 1748. He was a clergyman and a physicist, French person. He demonstrated what is osmosis. So we know that osmosis is a natural phenomenon. And in the process of osmosis, usually the solvent molecules, if they are separated from a high concentrated solution by a semi-permeable membrane, I can just show it. This is that I have prepared, a simple understanding purpose. So this is the semi-permeable membrane, the dotted line I am showing. And two solutions are separated. And one side is obviously more concentrated, you can see more number of the white will represent the water. The other side is obviously dilute. So what will happen? This is a natural phenomenon. So this barrier layer will selectively allow the movement of the solvent. So we can see this generates the pressure that is called the osmotic pressure. Because of this pressure, it will reach this water level will go up here and the water level will come down here. So this was the initial position. Now this is the final position. Now what will happen if we apply a pressure with this piston just to bring back the equality? This will be the, so the pressure applied is just equal to the osmotic pressure. And in the case of reverse osmosis, if we apply more and more pressure, then what will happen? This water molecule from the concentrated side will now move to the dilute side. It's the reverse of the osmosis process. So this thing was first time demonstrated using a bladder, natural pig bladder probably. And thereafter, of course, everybody almost forgot this osmotic process and all other things, no use. But desalination unit that was available. That was made available only in 1885 as a unit. And the credit goes to one, I think it's a French person, but he was in Britain. So one patent was granted in the same year, 1885. That was a vertical tube-like structure, which was really giving, its desalination was possible through that structure, and it was, I think, 70,000 gallons, 7,000 gallons per day. So that was that was totally based on that thermal distillation process. Before that, in ships, people used to boil water and collect the vapor and condense it and used to drink. So in that way, desalination was done. But this was only first time in a very organized way, I will say. And during that period, of course, the steam engine came after industrial revolution. So in ships, the thermal desalination became popular. So only after the Second World War, I realized I should a goal. I mean, how to eradicate that problem. So John F. Kennedy government goes to see only in the year 1959. This was the 1959. 1978, 59 to one membrane, polymeric membrane, which could desalinate water. So that was the first reverse osmosis membrane, and a process developed on the basis of osmosis phenomena. And just one important point I'd like to share. I couldn't find any information about this gentleman, Srinivasa Shoryarajan. is still living. Sydney Loeb, of course, left in the year 2008. And Srinivasa Soryarajan, he must be up 98 now. He is in Canada. But we really don't have any information in internet. Only thing is we can find his papers and few patents. And everything is from the work of Loeb, or if we find something about written about Loeb, then only we get about Srinivasa Soryarajan. Otherwise, we really don't know anything. So if anybody can find any information, can share with me, I'll be very happy. So that membrane was cellulose acetate based polymer, using cellulose acetate based polymer. So they prepared a membrane which could desalinate. Now, that was a very interesting thing, and that attracted many other industries also. Though thermal desalination was there, but people suddenly realized the importance of the thing because energy requirement was much less compared to the thermal desalination. And immediately in California, in the year 1965, they established a pilot plant. Immediately, only 1959 this was discovered, and 1965 the pilot plant was installed in California, and that was producing this 76, I can 76, 7.76 tons. 3 years that produced this much gallon of water, and salt rejection was, of course, not that good. Usually, seawater salt is around, it starts with 33 to 42,000 ppm. So only 89% was the salt rejection, but still, that is very good. So immediately, government also shown their interest. So a particular research institute was given this task, and it was formed, North Star Research and Development Institute in Minneapolis. And this gentleman, Peter S. Francis, I have shown one. I could only find one photograph of this gentleman. He was actually a chemist in a powder company, and his research interest was about the tablets, pharmaceutical company tablets, coating of the tablets, all these things. So he was given the chance in this institute to further develop the membrane. And I have particularly chosen this photograph because he has given a very important concept, that is the composite membrane concept. The composite membrane, what are the composite membrane? In very short, I would like to say. Usually this is the cellulose acetate based structure, cellulose structure. And when cellulose, we prepare membrane from cellulose, then it becomes a asymmetric structure. Or asymmetric structure means the top layer will be the denser, and the bottom layer or the middle layer, they will be porous, more porous. So this was the asymmetric membrane and cellulose acetate based membrane. I'm just saying, this is a real photograph. We can see the top layer as very dense and the open layer in the middle or in the lower side. So he has given the concept of this composite membrane. Why not to make two different layers, like a dense layer and a porous layer, and just to laminate them? What will be the benefit? The benefit will be we can work with the two layers separately. We can optimize the lower layer, and also we can optimize the dense layer, and that will give us more flexibility. So this concept was given by this gentleman, and the work was given to Cadot. I don't have any photograph of Cadot. I couldn't find. So Cadot developed really the composite membranes. So cellulose acetate was used as the top layer, and different other polymers were used as the bottom layer or the support layer. Now, I have mentioned polysulfone. The polysulfone was, Cadot used polysulfone, and it was such a good material, engineering material, that still now everything is almost established. Still now, polysulfone is the first choice. And all the membranes, composite membranes, are actually all reverse osmosis or nanofiltration membrane. These are all supported on a polysulfone-based ultrafiltration membrane. So Clark's also improved a lot. Soryarajan membrane was giving 3 GFD, and now it is giving 5 times. And certainly, the rejection also improved. And we probably know about the film tech company. And this film tech company is, they are ultimately dominating the membrane market in the, even today also, film tech and DuPont. So it is a part of Dow. They became the North Star Institute, which actually developed this composite membrane, became the part of the film tech company. So this is the contribution of Cadot. I'm just saying in a simple way, this gentleman, Morgan, so he conceptualized the interfacial polymerization. So interfacial polymerization, that is nothing but two different solvents are taken, which are immiscible. Now, one monomer is taken in organic solvent, the other monomer is taken, suppose, in aqueous solvent. Now, organic and aqueous, they are immiscible, so they will meet somewhere in the interface, and that interface will be very fine, very thin. And we choose the monomers in such a way that they are highly reactive to each other, but they cannot react directly because one is in organic media, the other one is only in the aqueous media. So only at the interface they come in contact. So a fine film is formed, and that film is actually put on the support film, like here I'm showing. Suppose this is how we are making the polysulfone membrane, one support, that is a fabric, top of that polysulfone membrane, and then this is thin film made separately and it is placed on the top of this. This is the composite membrane, and which is, I mean, today also we are using the same kind of membrane and same chemistry. So this was, the phenomena was discovered by this gentleman, Morgan, and Cadot used that. So these are the different types of membrane we automatically, I mean, these are all commercialized membrane, PA300, RC100. So these were developed during that period, 1970 to, I will say, up to 80. This piperazine based membrane, this is one monomer, and this is the metaphenylaline diamine. These are still used and probably the only combination which is commercially very successful. And all the reverse osmosis membranes are actually combination of metaphenylaline diamine and trimethyl chloride. They form the top layer. And if it is a nanofiltration membrane, people choose piperazine, not metaphenylaline diamine. So these things, everything was discovered before 1980. So the flux also increased. You can see 29 to 42 liter per meter square and per hour. And salt rejection 99.1 to 99.5, or now it is 99.7. So 1959, the reverse osmosis membrane was first time made, and by the 1978 or 80, almost all the work were done. And so far, there are some modifications of the membrane, but the base work remains same. And actually, already rejection reached 99.7%. So hardly few left, and that is not possible also. 100% rejection is not possible. So this is the scenario of the, I will say, the seawater desalination worldwide. Nowadays, now there are 19,000 plus desalination plants. I didn't say these are all membrane based. They are desalination plants. So seawater is desalinated. So this is the capacity of different, very big desalination plants. Most of them are in the Middle East. You can see these are almost all of them. And only, you see the capacity, 1,000 million liter per day. It is a combination of RO and MSL. MSL is a thermal based technology, that is multi-stage flash distillation. And Soeba, they are also, you will see, thermal based and RO. Actually, what happened? Of course, this Saudi Arabia, United Emirates, they were always water stressed country. They didn't have the very good source of fresh water, so they were depending mostly on thermal, because that time even the reverse osmosis membrane that didn't come. So before that, they started membrane desalination that was thermal based. In addition to that, they have plenty of oil, fossil fuel. So that cost of energy was, in a way, they could bear the cost of energy. So most of the plant, they started with thermal desalination, but with time, they have expanded those plants. And all the new installations are mostly, I mean, all the expansion work are done based on RO method. Now it is increasingly becoming favorable. So this is Fujairah, not Fujairah, I will say this Jubilee plant. This is the 600 MLD plant, which is completely on RO based, but it will be completed by 2022 next year. And probably Ashkelon plant, I didn't mention here, Israel, that was the first complete RO based plant. So it is becoming, desalination is increasingly becoming useful, and RO is becoming more acceptable. So now 69% plants are actually plants, and 18% these are multi-stage flash distillation, and 7% of the plants in the world are multi-effect distillation. Multi-effect distillation is another thermal technology. Rest of the plants are like nanofiltration, electrodialysis. Those are some other desalination methods. So this table shows one thing, that if we see the distribution of this plant, these are mostly in Middle East or East Asia, Pacific, North America. So one thing is that 47.5% of the desalination capacity, that's million liters, million cubic meter per day water is produced in these areas, Middle East and North Africa. Immediately East Africa or East Asia and Pacific, all these are less. You will see one thing, that actually these countries are very high income group countries. So desalination of water, obviously it will involve some cost. And when cost is involved, obviously the low income groups, even if they have some scarcity of water or water stressed in a way, they don't have fresh water, but still probably they cannot bear the cost of desalination. And nowadays, of course, the price is decreasing, but still it is not free water, I will say. So this is the worldwide situation. If you see the Gulf, they are accounting for 61.4%. So 61% seawater desalination capacity is in Gulf. But brackish water, it is North America, 36%. And in India also, of course, there are only two, I will say, the plant which is supplying water to the Chennai municipality, but there are other three plants which are very big plant, I will say, and one of them is really big. Those are for the private parties. So India accounts only 2.2% of seawater desalination, whatever desalination capacity we are having, and 4.4% is for brackish water, and 2.3% is for that is only for wastewater treatment. So now the question comes, the cost. What contributes to the cost of desalination? Now, everything in terms of electrical energy we have converted. So if you see that now then I need to understand a little bit about the MSF and MAD process. In multi-stage flash distillation and MAD, that is the multi-effect distillation, they usually in multi-effect distillation they use steam, and the seawater is sprayed on the steam tunnel. Automatically the water becomes hot and a part becomes gets vaporized, and that vapor is collected. Not that vapor is again passed through a cold water to a tube. Then again it vaporizes the cold water. So in that way, in different steps, it vaporizes water, vapor gets condensed, and we collect. So that is the multi-effect distillation. Now in multi-effect distillation, since the steam is involved, so automatically it involves a thermal energy. And similarly in multi-stage flash distillation, what they do, they hit the brine, and then what happens, the brine enters in different chambers with decreasing pressure. So when only at atmospheric pressure water boils at 100 degree centigrade, but when the pressure is less, automatically water will boil at lower temperature. So in that way they increasingly decrease the temperature, and water what happens, that when it enters in the one chamber where the pressure they maintain is less, so the whatever temperature maybe the brine is carrying, that remains always above the boiling point. So automatically to attain the equilibrium process, it flushes out the vapors. So that vapor they collect. So in different stages they collect it. So ultimately it involves your thermal energy. So if I see the energy distribution here in MSF, the total volume in terms of cost, 29% of the cost is for the thermal energy, and in multi-effect distillation, the 37% of the cost is because of thermal energy. Electrical energy is obviously required everywhere, so that also accounts in multi-stage flash distillation 18.7%, and MED it is 7.2%. Only advantage in RO process is they don't need thermal energy, so only the electrical energy is required, which is 31.6%, and that is the main reason why the cost is reduced. So if we see that for multi-stage flash distillation, the desalination cost is $1.07 per cubic meter, and it is less than $1 in multi-effect distillation, and in RO system it is coming around $0.76. But these figures are not fixed. It varies in region to region depending on the life cycle of the plant, how old is it, whether it is maintained, probably different factors, and water quality obviously. So when this is compared, so RO automatically, energetically, it is becoming less demanding. And that's why it is becoming acceptable. Now, since I told that those Middle East countries, they had the plants from the, I mean, since 1930 probably, or before that, that time RO was not there. So they had thermal plant, and still they are working with that. They are doing with the RO plant for desalination purpose. So another point is that we often have a concept that RO water is very costly. The question is how costly. So this is the answer. The cost is actually per cubic meter. If I see, this is here we have mentioned the $0.76 per cubic meter, but it ranges actually. If I see, that comes around 45 to 50 rupees per 1,000 liter. I'm not considering this one, but this is a standard calculation. It's coming around that much only. But still, it is not free. Certainly, it is not free. Now, what are the cost components? If I consider the RO system, then the fast desalination, where it takes a fast pass, that is the consuming maximum energy. Because in that, I'm just giving one example. This fast pass means the raw seawater after treatment, all pre-treatment and all these things, then it is first filtered through a membrane, then maximum energy is required there. In the subsequent passes, if required, the water may be refiltered, but there the initial feed concentration remains maybe around 1,000 or 2,000 depending on the plant design. So initially 42,000 to 2,000, and later from 2,000 to below 500, it may be 300, 200, and then in some countries they again treat the water, they add minerals to it. So those steps are not really energy intensive. The first step of RO filtration is only energy intensive. Now, what is the minimum energy required to desalinate seawater using an RO membrane? So obviously, it will depend on the osmotic pressure. So we'll have to apply pressure above the osmotic pressure, then only desalination will take place. So thermodynamically, it has been calculated for seawater desalination to occur, we need actually 1.1 kilowatt hour per cubic meter. So that is the only energy requirement. But at this energy in the real system, it goes up to minimum energy. So for recorded is 2. It is 2 kilowatt hour per cubic meter. And this is the actual case, but only energy required to achieve desalination in real case is 1.5, but in plant level it is 2. Then still I'm showing that in this table 3 to 7 kilowatt hour per cubic meter energy is required. for desalination, because the other systems like the pumps, they are using intake pumps, water intake pump, pre-treatment, and the auxiliary equipment, post-treatment, product water pumping. That is consuming 0.58 kilowatt hour of energy per cubic meter. So those are adding cost. So if we want to reduce the cost of desalination, yes, certainly we'll have to go for a better membrane materials. Okay, but that will hardly reduce it from, I will say, 2.3, suppose 2.3 to, it will come down around 1.2, I will say 2, or maybe 1.8 or maximum. But that's why other things like the pre-treatment, intake, the efficiency of the pumps, post-treatment, and water distribution, those things are becoming increasingly important. Now, people are working on those areas to reduce, other than this membrane material, they are working on those areas to reduce the cost of the desalination process. Now, Spain is also, water stress, and they don't have fresh water much. So since 1970, the way the price decreased in the energy consumption decreased. This is a Spanish experience. In one of the paper they have published, it was 22 kilowatt per cubic meter in 1970, and 2009 it is less than 3 kilowatt hour. So these are the different factors that really improved, like the membrane performance and availability and choices. Now we have different types of membrane. Like if you want a high rejection membrane, yes, it is possible. If you want relatively low rejection but more productivity, yes, it is also possible. If fouling should not occur, yes, that is low fouling membranes. So this kind of different, and even ultra low energy, you need very little pressure. So compared to like 900 psi, or now people can even operate at 800 psi, less than that. But different types of membranes are possible, and they're active. Then one more thing is the plant design. So there is a lot of I will say improvement in engineering designs. Like these are different types of plants design. A simple way I have mentioned, like it is a single pass system where the feed will enter and you will get the permeate and the reject will be rejected. But in two stages, the reject can again be treated to get the permeate. So in that way, you are increasing the water recovery, which is also very important. How much water? Suppose you are taking 100 liters of water, if it is a seawater membrane, seawater desalination, then nowadays we can still recover maximum 48 liters or 48 liters. We couldn't go beyond that. Brackish water is at TDS around 500 to maybe 15,000, very high brackish water, but usually in the range 2,000, 7,000 for drinking water use. So there we can still attain 70 to almost 90% recovery. So water wastage is also less in that case. So this type of design, different kind of design, has to cost of desalination. Pre-treatment, pre-treatment is another very important fact, because if you, a membrane, which is a thin film composite membrane, reverse osmosis membrane, whatever, that is made to filter salt from water, filter out the salt from water, not the other things. There should not be any coarse material, coarse particle, or there should not be any macromolecules, because they will simply block the pores. They will simply block the membrane. So membrane productivity will get down. So it will be reduced. Once the membrane productivity is reduced, we need to clean the membrane. So I need more chemicals. Then chemical will again add to the cost. Then after washing repeatedly with chemicals, the membrane itself will lose its integrity. So a time will come when we need to replace the membrane again, and the replacement cost is very high. So that pre-treatment is very important. So before going inside the membrane modules, the water should be treated properly. It should be free from bacteria. It should be free from all macromolecules or any suspended particles, anything, and scale formal. There are like calcium, these things. So during the pre-treatment, all these things are taken care. So with the development of pre-treatment process, the cost has reduced again. Energy recovery device. That is very important. I'm showing this yellow part. That is the energy recovery device. What happens that when we are pressurizing water, suppose at 800 psi, that is around 55 bar or to 60 bar, then the product of water is coming out, that is fine, but the reject water carries a lot of energy that comes out with a high pressure. So if we can make use of that energy, so the exchanger use that energy, they transfer the pressure from the reject water to the feed water again. So you don't need to pressurize the feed water up to 800 or 900. You can pressurize the feed water up to 400, not 400, around 600, and the rest 100 to 200 psi pressure that can be reclaimed from that that is called reject water. So in that way, that is reducing the energy cost. Actually, 60% of the energy cost is reduced by the use of the pressure exchanger. So that is a very important thing. Module design and how they placed. Just example. So earlier they used to place only one module inside the pressure vessel. Now they are putting several modules. So there are many advantages of placing this kind of several modules. So I'm not going into the details, but at least we can see now that that inlet, at this inlet only we need at both the ends, closer or coupler. In between, we don't need. So that is reducing the cost. Because there are 7 means we need in a single arrangement, single module in single case, we need that sort of 14 coupler, but here only working with 2 couplers. So that is also reducing the cost of the process. And also, if we recover, suppose our target is 1000 liter per hour, and with minimum volume of water, feed water, if I am recovering more water, means I will gain profit. Otherwise, I will have to continue the process for a longer time to achieve my goal. So that water recovery increased in different way. This is another combination by combining modules, then placing the pressure vessels, then maximum utilizing the energy. So in that way, so the energy requirement for desalination process that also reduced. Now, this is the cost of desalinated water in different places. Like I consider Algeria, Australia, China, Cyprus, India, Israel, Saudi Arabia, Singapore. You can see the cost. It is mostly around 0.7, 0.6, depend on the geography, location. This Australia, it is coming around 1.17, of course. Then most in India, it is coming around, I think 1.03. Yeah, $1.03 per cubic meter. That is 1,000 liters. So this is the, but these plants, like this plant is costing only 0.49, 0.36. These are actually very big plants. So those big plants actually operate at most cheaper cost in different ways. It is all engineering things actually. So seawater pre-treatment, I would like to give some importance to the pre-treatment, because pre-treatment, you see that pre-treatment itself accounts for 12% of energy consumption, and it's a very important thing, because if we don't treat our water at the pre-treatment level properly, it will reduce the productivity of the plant, and I said that it may damage the membrane, and then we may need to replace the membrane. SWRO, seawater RO replacement cost is 6% of the total operation, total plant cost, if we see. So we always, one membrane lasts usually for 3 years, and if proper care is taken, 4-5 years maximum. So this pre-treatment should be very important. So I'm discussing this pre-treatment part a little bit. This is one typical pre-treatment chain I have shown. Like this is the raw seawater intake point. Then there is screening is done, all the suspended solids and all other things they are removed. then it's pumped, then there is a dissolved air flotation, then due to the oxidation, air flotation, so automatically spots are formed on the top, those are removed, then it enters into the pump, and then again straining, and then membrane filtration. I'm showing all these things because, like when I did my MTech in energy technology, I was having no idea that I will be working in this field, but I had the opportunity. And later I realized, okay, this is a nice one. So many people, many students may find it may be interesting for them. So I'm showing these things. Not only the chemist and engineers are also very interested. Multidisciplinary subject. So it may be interesting for everyone, and everyone is having scope actually to work in this whole process. And this is the SWRO membrane. Actually, I work here only in membrane part. I don't work in this part, very little. So this is one very important thing, subsurface intake. You see, I'm showing one figure. What is subsurface intake? Seawater at the bottom level, I mean at certain depth, it is much cleaner than on the top level. And temperature wise also it is much lower than on the top level. So now what they are doing, they are taking water from deep sea, so that they are getting better quality water, cleaner water, and at the same time temperature wise also low, and they are avoiding all the suspended particles. I'm showing another figure here. What happens when algal bloom takes place? You see, the whole surface water is covered by this algae. If it enters into the system, then it will choke the whole process. So to avoid that, also this deep sea pump are more useful. If you take water from the deep sea, you can avoid all these things. So these are all small things that contributed to reduce the cost of operation in the process. See, yes, reverse osmosis with less desalination that consumes less energy, but still, whatever energy it is consuming, it finally depends on the fossil energy. So far, but if we can use the renewable energy sources, then it should become even more cheaper. But nowadays, it is not cheaper. There are many plants, but still, good number of plants. Out of 87 indirect solar desalination units installed worldwide, 52% are out. But the main cost is presently contributed by the additional capex and opex. They are the major cost contributor. Additional capex and opex is for the, suppose if it is a PV based or wind power based, then we need to install those things. So that will add to the cost. Otherwise, with time, it has been calculated that maybe in the year 2030, it will become parallel to the fossil fuel driven, not thermal, but RO processes. It will come around 0.85 to $2.43 by that time. But right now, this is not possible. This is not really competitive, renewable energy driven plants. But with time, it will become certainly competitive. So this is even just to mention here that we have also installed one RO plant, which is solar energy based in Rajasthan. Like it is operational. Now, brine management. Now, there is another problem. I will say that people often say that RO-based desalination technologies are highly polluting in nature. What will happen to the reject? See, when the reject, you see, the seawater is 42,000, let us consider. Automatically, the reject will become nearly 70,000 ppm. So this is a very high salt concentration. So what is happening nowadays, the common practice is they are throwing it to the sea. So automatically the environmentalists, they are now questioning. So you are throwing it back to the sea, and so it is creating some problem in at the local levels, ecology level, it's destroying the local ecology. But I don't know this fact because people are still working on that. So in this map, all desalination plants, seawater desalination plants, which are actually placed very near to the coastal zone, with 10-kilometer maximum distance, mostly in the coastal zone. So what they do, they are rejecting that reject water, throwing back to the sea. What happens now? See, if I consider the volume of water I'm removing from sea and I'm throwing back, so probably it will never. It is infinitely small. I will say very small volume. So it should not create any problem once the salt is going back to the sea, and if the salt was originally present in the sea, but it may create some local issues. Um, so what I will say that the brine volume generated is significantly very high, 141.5 million cubic meter per day. So it's a huge volume of brine which is going back to the sea. And so that may create some problem, but I'm giving you some example. So these are some of the things I have shown. They have observed that some of the species that disappear when there was a excess concentration at the local level. But with the introduction of another technology that is called diffusers, those things came back. Those lost ecology, they could re-establish. What is the role of a diffuser? The diffuser at the point where the water is released, this reject water, concentrated water, that spreads around so that the concentration gets immediately distributed in the whole sea, or at least the near vicinity. So they are restricting the effect maximum of 200 to hardly 1500 meter, even not 1500 meter. When they use a single diffuser, the concentration gradient remains up to 1500 meter. But when they are using double diffusers, they have observed that in many cases, in most of the cases, the concentration gradient that remains limited within 200 meters. So only you can say in a way that equality of the 200 meter radius area that will be disturbed, not beyond that. And nowadays, even they are mixing the reject water with the water collected from the thermal power plant, because most of the desalination plants are also connected to thermal power plant. So mixing with the coolant water, and then they are diluting the water. And sometimes this particular figure I have shown. So there, Carlsberg, what they do, there is a very much, I will say, the mix the reject water with the sea water at the outlet point itself, and the mixing takes place in such a way, actually the surface water salinity remains below 34 ppm within 250 to 200 meters, not more than that. So there are different techniques actually which is reducing or minimizing the effect of this reject water. But still, it is people are studying now if there is any more effect or not. So there are different technologies which are coming forward to treat this reject water. The most promising one is your vacuum membrane distillation. So the reject water is again distilled, and when vacuum is applied, so at very low temperature, this forms vapors, and the vapor passes through the membrane, collected on the other side where it is condensed. So you can also, not only you are managing the reject water better way, we are also collecting more water, so that will also increase the recovery of the plant. But all these technologies, these are mostly at the pilot scale level or at the R&D level. Only the vacuum membrane distillation is to the pilot scale. There is no commercial plant based on that, on this technology. So now our scenario, that national scenario, if I 82% of the rural households in India do not have individual piped water supply. Fine. And 163 million live without access to clean water close to their homes. Now, India is also a water stressed country because we are extracting more than 80% of the groundwater. There are only 2 plants which are working for the people. That is Nirmal plant and the Minjur plant in Chennai. And those two plants can only make 25% of the Chennai water requirement. Each plant supplies 100 million liters, but with time, now more government is coming forward, like Andhra Pradesh, Maharashtra, and Gujarat. They are considering this option of seawater desalination more seriously. In Gujarat, I attended 2 meetings. Then we observed that finally, when the tendering process is also completed, and Gujarat is of course not going for any very big plant. They are going for small plants, and but multiple number of plants at the different coastal region, just to avoid the pumping cost. Because we are having in Gujarat this pumping system is there. Narmada water they pump throughout Gujarat, but the thing is the cost is becoming very high. So they are now considering that small plants in the locality based plants. But in India, there are 2 or 3 other plants. Like one plant is here in Bhavnagar itself. The Nirmal plant capacity is, I think, that is 25 million liter per day, and there is one more plant is there. Plant. They are also having one plant that is also around 20 MLD plant. Only big plant that we are having in India, that is the Reliance plant in Jamnagar. The plant capacity is 400 MLD plant, and that too a hybrid plant actually. 160 MLD is maintained by the thermal desalination process, and the rest is by the RO process. Most of the plants are based brackish water plant. In CSIR, we have also installed more than 150 plants across the country. Only 2 of them are seawater, small scale, like 10,000 liters per hour capacity. So my conclusive remarks, that will be that seawater, certainly that is an option which can supplement the water through desalination process. The thing is, even that desalination process, whether it is thermal based or will consume energy, and automatically it can be for countries like ours and many other countries, undeveloped or developing countries. Probably we cannot really directly afford this cost. The thing is, we'll have to save water and we'll have to recycle water. We'll have to work in that direction also. If we renewable energy sources, that renewable energy is also not equally distributed everywhere. So that constraint will remain probably. What I feel, that constraint will remain, like the fossil energy. So ultimately, not only the water desalination is fine, but we'll have to work more to save water and recycle water, and if we can minimize the water utilization. So with that, I would like to thank you all. And now I think we are left with some time so that we can have discussion. I'll be very happy to take part in this discussion.